In problem 5, a right circular cylinder is inscribed in a cone with height 1 meter and base radius 1 meter. What's the largest possible volume of such a cylinder? So we have a cone, and inside that cone we're going to inscribe a right circular cylinder. Now the height of the cone is 1 unit and the radius of the base is 1 unit. So you might see that in there you have similar triangles being created with the from the center, which is a common center to both the cylinder and the cone, and the height of the cylinder there. So you might be able to picture then that when the height of the cylinder is smaller, then you're going to get a wider cylinder there, and as you continue to increase the height, the radius of the cylinder is going to decrease until you get to the point where the radius is 0 and it is just a line there going from the vertex down to the base. But if we used a pair of similar triangles to try to reduce the number of variables in the problem, we would get something like this. We know that the height of the larger triangle is 1 and the base of the larger triangle is also 1. Now if the line represents the height, the line in the middle represents the height of the cylinder, then the height of the smaller triangle on the top would be 1 minus h. And from this we would get the relationship. Sorry, just one more thing. The line going across is also the radius of the cylinder. And so the ratio 1 minus h to r is equal to 1 over 1, and we cross multiply to get r is equal to 1 minus h. So if we substitute 1 minus h for r, we will always get a right circular cylinder that is inscribed in the cone. And at this point we can begin to find the volume and where the rate of change in the volume of the cylinder is going to be 0. So you start off with the height being 0 and the radius equal to 1 with 0 volume, and then you're going to slowly shrink the radius and increase the height, and you're going to increase volume until you get to the point where the radius is 0 and the volume is back to 0. So we want to find where the volume, the rate of change of the volume, becomes 0, where it stops increasing and starts decreasing. So if the volume of a cylinder, right circular cylinder, is pi r squared h, and the fact that it's a right cylinder, circular cylinder, only means that its sides are perpendicular to its base, which is a normal cylinder. So if we swap out the r and replace that with 1 minus h quantity squared, we would get pi times the quantity 1 minus 2h plus h squared all times h. Simplifying again, we would get pi times h minus 2h squared plus h cubed, and at this point we can differentiate with respect to h, and that would give pi times 1 minus 4h plus 3h squared, and that will be 0 when I factor that expression to get pi times 3h minus 1 times h minus 1. So at h equals 1/3 and at h equals 1, the volume, the rate of change of the volume will be 0. So it starts out increasing. At h equals 1/3 it starts to decrease, and at h equals 1 it becomes 0 again because there is no more volume. But we don't want when h is equal to 1. At that point there would be a 0 volume there. But when the height is 1/3, the radius is 1 minus the height, which is 1 minus 1/3 is 2/3. So the volume will be pi times r squared, which is 2/3 squared, times h, which is 1/3. And we would get that the volume is pi times 4/9 times 1/3, which is 4 pi over 27. And that would be in units cubed, whatever the units were. Here they're meters, so meters cubed. And that should do it for that problem.